Section 1.7 Atomic Properties, such as atomic radius, ionization energy, electron affinity, electronegativity, polarizability. First, let's talk about the atomic radius. Both metallic radius and covalent radius are considered atomic radius. Let's look at some pictures. So these two are metallic atoms. The distance between the two nuclei is 2 times the metallic radius. This is a homonuclear diatomic molecule, such as H2 or F2. The distance between the two nuclei is also 2 times the covalent radius. The atomic radius depends mostly on the effective nuclear charge. The effective nuclear charge in the fluorine atom is much greater than that in lithium. That's why this fluorine is smaller than lithium. The electrons are more attracted to the nucleus, so even this fluorine atom has more protons, more electrons. It's smaller than lithium. It has a smaller atomic radius. Now let's look at the ionic radius. Let's look at this example. Imagine this is the sodium plus, this is chlorine minus, and then the distance between the two nuclei is the sum of the ionic radius of sodium and that of chloride. So that's very simple. Ionic radius depends mostly on the charges. So if you have a plus charge, that makes the ion really small. If you have a -4 charge, that makes the ion really big. This also is related to the effective nuclear charge. Well, if you have aluminum 3+, of course, there's a very large, very positive, effective nuclear charge felt by the valence electrons. So aluminum 3+ is really small. And then, of course, you can think of some ions with -2 or -3 charges. For example, oxygen 2-, nitrogen 3-. They are really big, not because of the numbers of electrons. It's just because these electrons feel very small effective nuclear charge. They are not really attracted to the nucleus that much. They are repelled by other electrons. That make the ionic radius really big for oxygen 2- and nitrogen 3-. Again, it does not depend on the number of electrons. Do not count the number of electrons. Focus on the effective nuclear charge. Well, there's another factor. Actually, that's the principal quantum number. Of course, the larger the principal quantum number, the larger the atomic radius. This is also because of the smaller attraction between the valence electrons and the nucleus when you have one additional shell. Now let's look at the table of atomic radii. Roughly speaking, you have fluorine has the smallest atomic radius, cesium has the largest atomic radius, and the trend is from top left to the bottom, top right to the bottom left. So largest, smallest, and then if you compare sulfur and phosphorus from right to left, again from right to left you have increasing atomic radius. From left to right, increasing atomic radius. From top to bottom, you have increasing atomic radius. Of course, in the transition metal block, you have exceptions. You have exceptions for many other reasons. This is also atomic radius. You can see periodic trend. When you go from lithium to fluorine, the atomic radius decreases. Again, fluorine has more electrons than lithium, but fluorine has a smaller atomic radius than lithium. So you have this trend decreasing and then decreasing and then decreasing. Over here you have transition metals in the middle, and there you can see some exceptions there. And again, transition metal over here. But overall, you see a decreasing trend. You see a decreasing trend. I think over here you see some F block elements. So you see more trends. You see more exceptions. You see more exceptions. But overall, in each period, from left to right, the atomic radius decreases. And then if you compare, the elements in the same group, and then of course rubidium is bigger than potassium, potassium is bigger than sodium, sodium is bigger than lithium. Same here, bromine is bigger than chlorine, chlorine is bigger than fluorine. So this is the ionic radii. If you look at lithium versus beryllium versus boron, you can see boron has 3+ charges. Therefore, the atomic radius is the smallest here. Same here. Sodium, magnesium, aluminum. Again, you can see aluminum 3+ is smaller than magnesium 2+. It's smaller than sodium plus. It's not about the number of electrons. It's about the number of effective nuclear charge. Alright, again over here, so you can see 3- charge, so this is really big. Only 2- charges, only 1- charge, so you can see the trend here as well. Again, nitrogen 3- is really big because of the very small effective nuclear charge. Electrons repel each other when you have 3 additional electrons in this 3- ion. Due to the repulsion between electrons, you have a very large ionic radii here. Now let's compare the elements in the same group. So 59, 99, 138, 148, 167. So it's going up from top to bottom. So why do we see multiple numbers for the same element? You can see if we're talking about a transition metal complex, then you can have different coordination numbers. If you put those ions, in the middle of ligands, all right, you can put this this cesium plus in the middle of 2 ligands, 3 ligands, 4 ligands, 6 ligands, 8 ligands, 12 ligands. You get different numbers, but overall the trend is the same. First, the ionic radius depends mostly on the charges. If you have a highly positive charge, and then you have very small ionic radius. Very negative, highly negative charged ions, and then you have very large atomic radius. And 2, it depends on the principal quantum number. The larger the principal quantum number, the larger the radius. Now let's look at the ionization energy. Look at the trend here. It's the opposite to the atomic radius. Right, from cesium to fluorine to helium. Well, again, depend on the effective nuclear charge and also the principal quantum number. The ionization energy is proportional to the effective nuclear charge squared. It's inversely proportional to n squared. Well, that's why actually this fluorine has a much larger ionic ionization energy than cesium, 375, 1681. And also, if you draw this arrow, you can realize this. From left to right, the ionization energy increases. Okay, from bottom to top, the ionization energy increases. Again, this equation tells you semi-quantitatively how the ionization energy depends on this effective nuclear charge and how this depends on the principal quantum number. Again, ionization energy from hydrogen to helium, and then from lithium to neon, from sodium to argon. You see the trends. Of course, there are some exceptions here and there. Those are mainly due to the half-filled subshells or completely filled shells. They are particularly stable. So if you look at this, you can see the ionization energy of nitrogen is actually slightly greater than the ionization energy of oxygen, only because in the nitrogen atom you have half-filled subshell. The 2p orbitals are halfly filled. That makes this nitrogen atom particularly stable. So it takes more energy to remove an electron from nitrogen. Conversely, it's a little bit easier to remove an electron from oxygen because there are 4 p electrons in oxygen. If you remove one electron, this oxygen plus can actually form a half-filled subshell. All right. Okay. Now more ionization energy. So this is this boron period, and you have second ionization energy. You have the third ionization energy, electron volt rather than kilojoule per mole. So let's talk about this first, second, third ionization energy using the previous table. If you look at this lithium, this is the first ionization energy. This is the second ionization energy. Look at these two numbers. They differ by a factor of 14. That's a huge difference. This is because over here we're removing the 2s electron, but now you're removing the 1s electron. We have this n equals 1. Here, n equals 2. So that's a big difference. And also, after you remove the first electron, if you're talking about the 1s electron has a much greater effective nuclear charge. Now for beryllium, you're moving these 2 valence electrons. And then this is the core electron. There's a huge gap between removing a valence electron versus removing a core electron. Boron, there's 3 are valence electrons. And this one is the core electron. That's why you see a huge gap here. Same for any other elements. First ionization energy. This is the second ionization energy. They differ by a factor of 8 because again, this we're talking about the 3s electron, but this is the 2s core electron. All right, so that's why. Electron affinity. Same direction here from bottom left to top right. Okay, so from rubidium to this fluorine. Don't worry about this noble gas atoms. They have a negative electron affinity because they do not like to accept electrons. However, fluorine does like to accept an electron. When a fluorine gets electron, energy is released. So fluorine minus has lower energy than fluorine. And if you have the energy of fluorine minus the energy of fluorine minus or fluoride, you get this 328 kilojoule per mole. Right? Even lithium welcomes an electron. So this lithium minus Ni has lower energy than the lithium atom. Well, again, this is because of the effective nuclear charge felt by the additional electron. All right, and then here's the trend with a lot of exceptions. Again, nitrogen is particularly stable with one half-filled subshell. The 2p orbitals of nitrogen are halfly filled. It's very stable. So if you give one more electron to nitrogen, you will break this half-filled subshell. Right? Beryllium. Beryllium has a 1s2, 2s2 electron configuration. So both subshells are completely filled, so it's stable. If you're given one more electron to beryllium, well, it makes it less stable. So that's why the electron affinity of beryllium is negative. For magnesium, it's also negative. For calcium, although it's positive, it's a very small number. So there are exceptions. But this is the overall trend from bottom left to top right. So again, get back to the noble gas atoms. They do not like to accept one additional electron because their subshells are all completely filled. Now, electronegativity is the ability to acquire electrons from other atoms Or if you have two atoms forming a bond, it's the ability of the atom to grab the shared electrons. All right. So, for example, if you have HCl covalent bond, chlorine has a higher electronegativity than hydrogen because two electrons are being shared by hydrogen and chlorine, but these two electrons are closer to the chlorine atom. So the electronegativity is proportional to the sum of the ionization energy and the electron affinity. Recall the trend for ionization energy is from bottom left to top right. For electron affinity, same trend, also from bottom left to top right. Therefore, the electronegativity is from bottom left to top right. Don't worry about the noble gas atoms. All right. So again, from cesium to fluorine, you have the smallest electronegativity to the largest electronegativity. And there are three different formulas: Pauling, Molekin, and Elrad. They all have an equation to compute the electron negativity. All right. This is the trend from lithium to fluorine. The electronegativity goes up. Same here, same here, same here. And in general, the electron negativity slightly decreases. Right, from fluorine to chlorine to bromine to iodine, so it decreases. And this is oxygen, this is sulfur, it decreases. Well, there are exceptions, from here to here there are exceptions. All right, so overall, the trend is from bottom left to top right, with some exceptions. Finally, polarizability. That's the ability of an atom or molecule to have its electron distribution distorted by an electric field, such as a neighboring ion or a dipole moment. So in this picture, I'm putting a positively charged ion close to this fairly large negatively charged anion. And the shape of this anion is no longer spherical, it's distorted. So this side is trying to get closer to the positive charge. In general, small, highly charged cations have high polarizing ability, so they can polarize other atoms or molecules. Large, highly charged anions are easily polarized, so fluorine minus can be easily polarized. Nitrogen 3 minus can be more easily polarized. And then phosphorus 3 minus can be even more easily polarized than nitrogen 3 minus, only because phosphorus 3 minus is larger than nitrogen 3 minus. If we're talking about molecules, again, in general, larger molecules can be easily polarized. So for example, if you have bromine 2, it can be more easily polarized than chlorine 2, than fluorine 2. So again, these two are general rules for you to decide what kind of ions can be easily polarized and what kind of cations have higher polarizing ability. Finally, cations that do not have a noble gas electron configuration, so mostly we're talking about D block elements. They don't usually have a noble gas electron configuration. They are easily polarized. For example, if we're talking about iron 2, so iron with 2+ charges, It does not have a noble gas electron configuration. It can be fairly easily polarized, or copper plus can be easily polarized.